1994. Severodvinsk, the White Sea coast of Russia. At the Sevmash shipyard, the industrial culmination of 3 decades of Soviet naval ambition was being finalized in the form of the K-141. Known to the Russian Federation as the Project 949I Ante, and to Western intelligence as the Oscar II class, this was not merely a submarine, but a 20,000-ton engineering statement. The ship was a high-performance mechanical system designed to solve a singular tactical problem: the neutralization of a United States Navy carrier strike group. In the cold calculus of the late 20th century, the Ante class was the ultimate predator, a mobile missile platform built to deliver an overwhelming saturation strike from the shadows of the deep. To understand the K-141, or the Kursk, one must analyze the specific industrial and architectural decisions that allowed a single vessel to carry the strategic weight of an entire fleet. The technical identity of the Kursk was defined by its massive scale and its unique double-hull construction. Measuring 505 feet in length and displacing 18,000 metric tons when submerged, the ship was wider and more voluminous than any attack submarine in the American inventory. This volume was not an aesthetic choice, but a requirement for its primary weapon system and its structural survivability. The ship utilized an inner pressure hull forged from high-nickel chrome steel, a material selected for its high yield strength and resistance to the corrosive environment of the high north. This internal skeleton was divided into 9 distinct watertight compartments, a redundant architecture intended to ensure that even if 1 or 2 sections were breached, the ship would maintain enough longitudinal stability to remain on a level keel. Wrapping around this pressure hull was an outer hydrodynamic hull, creating a mechanical architecture known as a double-hull design. To an elite marine engineer, the space between these 2 layers is more than a void. It is the foundation of the double-hull buoyancy reserve. This design philosophy separates the structural requirement of resisting deep ocean pressure from the hydrodynamic requirement of moving efficiently through the water. The outer hull provides the streamlined shape and houses the external sensors, while the gap between the hulls, the annulus, is filled with seawater. This configuration provides a massive displacement margin. Because the ship carries such a large volume of water between its hulls, it possesses a high degree of reserve buoyancy. In a standard single-hull submarine, a localized hull breach is often terminal because the displacement is tied directly to the pressure vessel. In the double-hull Ante class, the outer hull can absorb significant kinetic energy from a torpedo impact or a collision without compromising the atmospheric integrity of the inner pressure hull. The strategic heart of the Kursk consisted of 24 P-700 Granit cruise missiles. These were the primary offensive instruments of the carrier killer doctrine. To house these weapons, the naval architects installed 12 launch tubes on each side of the pressure hull, angled at 40 degrees within the annulus. This geometric arrangement allowed the missiles to be launched while the submarine was submerged and moving at speed. The Granit missile, designated by the West as the Shipwreck, was a 3-ton supersonic projectile capable of independent target acquisition and swarm logic. When fired in a salvo, the missiles would communicate with each other, with one high-flying missile providing radar data to the others skimming the wavetops. This was a system of synchronized violence, where the machine's architecture was optimized specifically to facilitate the rapid transit and deployment of these 24 heavy warheads. Powering this 20,000-ton machine were 2 OK-650B pressurized water reactors. These reactors were the mechanical descendants of the systems used to power Soviet icebreakers, selected for their high thermal efficiency and compact footprint. Each reactor generated 190 megawatts of thermal power, feeding 2 steam turbines that delivered a combined 50,000 shaft horsepower to two massive 7-bladed propellers. This nuclear metabolism allowed the Kursk to sustain a submerged speed of over 32 knots. The engineering required to dampen the vibration of these 50,000 horsepower systems was immense. To manage the acoustic signature, the outer hull was covered in a stealth skin consisting of thousands of rubberized acoustic tiles. These tiles were designed to absorb sonar pulses from enemy sensors and to muffle the internal mechanical noise of the turbines and pumps, turning the largest submarine in the Northern Fleet into a ghost of the Barents Sea. The engineering intent of the Project 949I was to create an unsinkable missile battery. Every system on the Kursk, from the high nickel steel frames to the redundant watertight bulkheads, was engineered to withstand the extreme hydrostatic loads of a deep-water patrol and the violent shocks of combat. The ship was a masterpiece of specialized metallurgy and thermal hydraulics, a vessel that functioned at the absolute limit of its era. As the Kursk entered active service, it was hailed as the pride of the Russian Northern Fleet, a machine that had seemingly mastered the laws of buoyancy and the physics of underwater speed. The ship stood as a balanced mechanical system, designed with a massive reserve of structural strength and a sophisticated double-hull defense. The architects at the Rubin Design Bureau believed they had built a vessel that could survive almost any localized failure. But the engineering of a warship is a chain of irreversible decisions, and the very features that provided the ship with its tactical dominance, the high-capacity torpedo tubes and the high-volume internal spaces, were governed by the unforgiving laws of chemical and pressure equilibrium. The Kursk was a predator without an equal, but its structural life was now tethered to the reliability of its internal ordnance and the integrity of the bulkheads that separated its 9 compartments. The ship was ready for sea, but the mechanical logic that judged it a carrier killer was about to be tested not by an enemy fleet, but by the volatility of its own hardware. 1999. The Mediterranean Sea. The geopolitical climate of Europe was defined by high-intensity conflict and the presence of massive NATO naval forces. In this high-stakes environment, the Project 949A submarine K-141 initiated a mission that was considered a mathematical impossibility by Western naval intelligence. To move a vessel measuring 154 meters in length and displacing 18,000 tons into the heart of the United States Sixth Fleet without detection is a task that defies the standard laws of acoustic probability. Yet, for several weeks, the Kursk functioned as a silent observer in a region where the density of sonar arrays and hunter-killer submarines made the water column an open book for NATO. This was the operational peak of the Oscar II class, a demonstration of how a massive cruise missile carrier could utilize its rubberized acoustic tiles to effectively erase itself from the tactical map. The strategic doctrine of the carrier killer was predicated on a specific engineering efficiency: the saturation strike. To an elite naval historian, the carrier killer is not just a label, but a calculated mechanical response to the dominance of the United States Carrier Strike Group. The technical challenge was to overcome the Aegis combat system, a defensive network capable of tracking and intercepting multiple simultaneous threats. The Project 949I solved this through the deployment of the P-700 Granite missile swarm. The math was direct. By carrying 24 supersonic missiles, a single Oscar II submarine could deliver more kinetic targets than a standard defensive screen could process in a 90-second interval. During the 1999 deployment, the Kursk practiced the geometric positioning required for such a strike, maneuvering within the acoustic baffle of carrier escorts to establish a terminal firing solution. This mission served as a forensic validation of the ship's design intent. The double-hull construction, which we have previously analyzed for its buoyancy reserve, proved to be an exceptional acoustic barrier. The space between the inner pressure hull and the outer skin acted as an isolator, preventing the mechanical noise of the primary coolant pumps and the geared turbines from radiating into the water column. The Kursk proved that she was not just an unsinkable missile battery, but a high-fidelity sensor platform. She successfully tracked the flagship of the Sixth Fleet, documenting the radio frequencies and acoustic signatures of the entire NATO carrier group while remaining a ghost. This achievement earned Commander Gennady Lyachin the title of Hero of the Russian Federation and solidified the Kursk as the premier strategic asset of the Northern Fleet. By the summer of 2000, the Russian Navy sought to capitalize on this prestige through the initiation of the largest maritime exercise in a decade, designated Summer 2000. The strategic objective was to demonstrate that, despite the economic collapse of the previous decade, the Northern Fleet remained a high-functioning industrial force. Over 30 vessels, led by the nuclear-powered battlecruiser Peter the Great, converged on the Barents Sea for a 3-day exercise of synchronized naval power. The Kursk was designated as the primary antagonist of the exercise, tasked with penetrating the defensive screen of the Peter the Great and executing a simulated strike with its 24 Granite missiles. The operational environment of the Barents Sea presented a unique set of mechanical constraints. Unlike the deep thermal layers of the Mediterranean, the Barents is a shallow shelf sea with an average depth of only 230 meters. To an engineer, this depth is dangerously modest for a vessel of the scale of the Kursk. At 154 meters long, the submarine was nearly as long as the water was deep. This limited the tactical maneuvering room and required extreme precision from the diving officers to manage the vessel's pitch and trim. Navigating a 20,000-ton machine in such confined waters is a study in hydrodynamic inertia. Every turn and every depth change exerted massive loads on the horizontal planes and the twin 7-bladed propellers. The maintenance of the machine during the lead-up to the exercise was a function of the Northern Fleet's rigorous dispatch discipline. Despite the age of the hull and the complexity of its nuclear heart, the Kursk maintained a near-perfect operational readiness record. Her 2 reactors were operating at high thermal efficiency, and her internal inventory of P-700 missiles was fully certified for combat. The crew, a mix of career officers and elite specialists, functioned as a single industrial unit, their lives integrated into the 9 watertight compartments of the pressure hull. They were operating the most sophisticated carrier killer in the world, a machine that had already proven its ability to outmaneuver the most advanced navies in the West. The tactical doctrine for the final phase of the exercise involved the use of a secondary weapon system, the Type 65-76 torpedo. While the Granite missiles were her primary strategic weight, these massive 65-centimeter torpedoes provided the ship with a localized defensive and offensive capability. These weapons were designed for high-speed engagement of surface targets, utilizing a liquid fuel system to achieve velocities of 50 knots. The handling of these weapons within the first compartment required a complex sequence of mechanical checks and pressure equalizations. For the Kursk, the torpedo was a secondary component in a larger system of carrier killing, but its integration was a mandatory condition for the success of the Summer 2000 sortie. As the Kursk transited toward her designated firing sector on the morning of August 12, 2000, the ship was a masterpiece of operational readiness. She had achieved her mission goals in the Mediterranean and was now the centerpiece of a fleet-wide demonstration of power. The engineering team monitored the 26 hydraulic strand jacks and internal valve assemblies that maintained the ship's equilibrium. Every system was nominal. The hull tiles were intact, the reactors were critical, and the 24 missile tubes were locked. The ship was functioning exactly as the designers at the Rubin Bureau had intended. She was a weapon of mass and placement, a machine that had successfully navigated the strategic noise of the Cold War and the technical noise of a changing era. The strategic peak of the career of the Kursk was a result of this mechanical alignment. For 6 years, she had served as a deterrent that NATO could not ignore. She was the pride of Severodvinsk, a floating fortress that had mastered the art of the undetected intercept. But the machine was now entering a tactical envelope where the margin for error was dictated not by the enemy's sonar, but by the chemical and structural boundaries of its own internal systems. The ship was in position, the targets were acquired, and the technical logic that had guided her through the Mediterranean was now focused on the launch of a single training weapon. The Red Castle was ready for the final act of the exercise, unaware that the engineering memory of the ship was about to be redefined by a sequence of events that no double-hull buoyancy reserve could prevent. August 12, 2000, 11:28 in the morning. The Barents Sea was the site of a mechanical betrayal that would redefine the limits of naval survivability. The flagship of the Northern Fleet, the Kursk, was in position to launch a training weapon as part of the summer 2000 exercises. This was intended to be a routine demonstration of the carrier-killer doctrine, but at that precise coordinate in time, the machine entered a state of terminal system failure. To a naval architect, the loss of the Kursk represents the ultimate logical paradox. A vessel engineered with a massive double-hull buoyancy reserve and 9 watertight compartments was effectively neutralized and dismantled from the inside out. The ship did not succumb to an external kinetic strike, but to a sequence of irreversible chemical and seismic events that originated within torpedo tube number 4. The catalyst for the catastrophe was the Type 6576 training torpedo. This massive weapon, nicknamed the Fat Torpedo due to its 65-centimeter diameter, utilized a propulsion system based on HTP volatility, or high-test peroxide. To an elite marine engineer, HTP is a substance of extreme industrial sensitivity. It is a highly concentrated form of hydrogen peroxide, typically 85 to 98% pure, used as an oxidizer to provide the torpedo with its 50-knot velocity. The chemical logic of HTP is based on its ability to decompose rapidly into superheated steam and oxygen when it encounters a catalyst, such as silver, copper, or even rust. This decomposition is a process of chemical autocatalysis, where the heat generated by the reaction further accelerates the breakdown of the remaining liquid, resulting in a geometric rise in pressure. The forensic reconstruction of the event suggests that a microscopic weld failure or a damaged seal in the torpedo's fuel tank allowed HTP to leak into the interior of torpedo tube number 4. Within the confined volume of the tube, the liquid peroxide encountered trace amounts of copper and iron oxide on the internal rails. The resulting autocatalytic reaction was instantaneous. The HTP did not detonate, it deflagrated, expanding its volume by a factor of 5,000 in a fraction of a second. This created a high-pressure gas spike that exceeded the design limits of the torpedo tube. The external hatch held firm, but the internal rear door, the only barrier between the weapon and the crew, was blown into the first compartment. This first event was recorded by the Norwegian seismic array NORSAR as an acoustic signal equivalent to a 1.5 magnitude tremor on the Richter scale. It was the sound of 200 pounds of high explosives, but the true kinetic energy was the pressure of the expanding oxygen and steam. The initial deflagration in the first compartment did not immediately sink the ship, but it initiated a catastrophic thermal environment. The high-pressure oxygen released by the HTP fueled an intense fire that reached temperatures exceeding 2,000 degrees Fahrenheit. This fire was located in the torpedo room, where the Kursk carried her primary combat inventory of 7 active warheads. The first compartment crew was likely incapacitated instantly by the pressure wave, leaving the ship without active damage control in its most sensitive zone. For 135 seconds, the Kursk existed as a ghost ship, drifting at a depth of 18 meters, while the thermal energy in the first compartment worked toward a terminal threshold. At 11:30 in the morning, exactly 135 seconds after the initial leak, The heat of the hangar fire triggered the secondary event. This was not a deflagration, but a massive, high-explosive detonation of the remaining torpedo warheads. The resulting explosion delivered a seismic shock equivalent to a 3.5 magnitude earthquake. To understand the scale of this event, one must visualize the release of over 5 tons of TNT equivalent energy within the confined architecture of the forward hull. This second explosion did not just breach the hull, it effectively disintegrated the entire forward third of the submarine. The high nickel chrome steel of the pressure hull, which was engineered to resist the hydrostatic loads of the deep, was shredded like paper by the internal pressure wave. This event marked the failure of the double hull buoyancy reserve. While the outer hull was designed to absorb external shocks, it offered no resistance to the outward pushing force of 5 tons of high explosives. The explosion traveled through the annulus and the internal passageways, shattering the first and second watertight bulkheads. The third bulkhead, located aft of the command center, was the first structure capable of offering any resistance, but the sheer force of the water rushing into the massive forward breach was overmatching. The Kursk was no longer a vessel. She was a perforated 18,000-ton girder, losing longitudinal stability at a rate that made manual intervention impossible. The trajectory of the loss was a high kinetic plunge to the seafloor. As the forward compartments flooded, the ship took on a steep downward angle. The 2 OK-650B reactors, which we analyzed for their icebreaker heritage, performed an automated emergency shutdown as the control rods were slammed into the cores by the seismic shock of the second explosion. This was an engineering success amidst the total failure of the ship. The reactors remained encased in their heavy lead shielding, preventing a radiological catastrophe even as the hull was being dismantled. The Kursk hit the seafloor at a depth of 108 meters with such force that the bow was buried 30 feet into the Arctic silt. The structural failure of the hull was compounded by the failure of internal communication. The shock wave of the 3-point magnitude event had traveled through the steel frames of the ship at the speed of sound, shattering light bulbs, crushing electronics, and severing the hydraulic lines that controlled the diving planes. The 1998 Mediterranean mission had proven that the Kursk was a ghost to the enemy, but now she was a ghost to her own fleet. The surface ships of the summer 2000 exercise had felt the tremor, but the technical logic of the era made it difficult for the Northern Fleet Command to accept that their premier strategic asset had been neutralized by a single training torpedo. By the time the Kursk settled onto the Barents Sea floor, the ship was a forensic ruin. The entire forward section, from the bow to the sail, was a tangled mass of thermally warped steel and unexpended missile tubes. The 9th watertight compartment, located at the extreme stern, remained the only pressurized sanctuary left in a machine that had been defeated by its own inventory. The strategic consequences of this loss were absolute. The carrier killer had been silenced by the very chemical volatility it required to operate its high-speed weapons. The engineering memory of the ship was now etched into the seismic tapes of Norsar and the crushed plating of the first compartment. The loss of the Kursk was not a tragedy of intent, but a tragedy of technical sensitivity. The ship was a masterpiece of specialized metallurgy and double-hull logic, yet it possessed an Achilles heel in the form of its HTP-fueled torpedoes. The mechanical trade-off for 50 knots of underwater speed was the constant presence of a chemical oxidizer that required zero-defect maintenance. On August 12, the margin for error within torpedo tube number 4 was exceeded, and the resulting chemical autocatalysis initiated a chain reaction that overmatched every safety system on the ship. The Red Castle was down, and the focus of the engineering logic now shifted from combat to the absolute physics of a deep-water extraction. The Barents Sea is a landscape of extreme acoustic and oceanographic noise, characterized by fluctuating thermal layers, high-velocity bottom currents, and a seafloor composed of fine glacial silt. To locate a specific target within this environment is typically a task of meticulous side-scan sonar mapping and probabilistic search grids. However, on the morning of August 12, 2000, the search for the K-141 was initiated not by a sonar operator, but by the sensitive needles of seismic monitoring stations thousands of miles away. The Earth itself had acted as a medium for the ship's final transmission. The problem of finding the wreck was not a matter of geographic uncertainty. The coordinates were effectively broadcast through the crust of the planet, but a problem of reconciling the seismic reality with the visual stasis of the seafloor. The primary forensic tool for the localization of the Kursk was the application of seismic acoustic fingerprinting. To an elite marine surveyor, a seismic event is a high-energy signature that travels through the seabed and the deep sound channel of the ocean. Unlike a standard sonar pulse, which bounces off the surface of an object, a seismic wave is generated by a massive release of energy that couples directly with the tectonic plates. At 11:28 and 11:30 that morning, the Norwegian seismic array NORSAR and stations as far away as Canada recorded two distinct spikes. This was the forensic timeline. The first pulse, measuring 1.5 on the Richter scale, and the second, occurring 135 seconds later, measuring a staggering 3.5. To understand seismic acoustic fingerprinting, one must analyze the velocity and frequency of these waves. Sound travels at approximately 1,500 meters per second in seawater, but it travels much faster and with less attenuation through the solid granite and basalt of the seafloor. By measuring the time of arrival at multiple geographically dispersed stations, analysts utilized a mathematical process known as triangulation. Each station provided a distance arc based on the signal's velocity. The point where these arcs intersected provided a coordinate for the energy release that was accurate to within a few hundred meters. For the Russian Northern Fleet, this meant they were not searching for a missing ship in the traditional sense. They were navigating toward a seismic epicenter. However, the transition from a seismic data point to a visual identification was frustrated by the navigation noise of the summer 2000 exercise. During high-intensity naval maneuvers, ships do not maintain static positions. The battlecruiser Peter the Great and the other surface vessels were operating under conditions of tactical concealment, and their own sonar arrays were frequently overwhelmed by the wash of their propellers. When the first seismic tremor was felt, it was initially dismissed by some commanders as the sound of a successful training launch or a distant practice depth charge. This creates a logical paradox in maritime search. The ship was found by the Earth instantly, but it took nearly 12 hours for the Naval Command to accept the data and initiate the localized search. The oceanographic environment of the Barents Sea shelf presented the next technical barrier. At the depth of 108 meters, the water is characterized by extreme turbidity. Turbidity is a measure of the amount of suspended sediment in the water, which scatters light and renders traditional high-definition cameras ineffective beyond a few meters. As the rescue vessels arrived at the coordinates provided by the seismic triangulation, they encountered a seafloor masked by a layer of fine silt that had been disturbed by the kinetic impact of the sinking 18,000-ton hull. The searchers were effectively looking through a cloud of liquid mud. This forced the team to rely on high-frequency imaging sonar to pierce the silt and identify the structural silhouette of the Earth vessel. Navigational uncertainty was further complicated by the drift models of the surface vessels. The Northern Fleet Command had to account for the discrepancy between the reported position of the Kursk at the time of her last radio check and the seismic epicenter. In 1942, navigation was a matter of dead reckoning, but in the year 2000, it was a matter of GPS and satellite synchronization. Yet, even with these tools, the exact resting place of the hull was elusive for the first 24 hours because the ship had not descended in a vertical line. The ballistic trajectory of the plunge, which we analyzed as a bow-first descent, had pushed the ship several hundred meters horizontally from the point of the second explosion. The search team had to walk their sonar arrays across the seafloor, searching for a hard acoustic return amidst the volcanic rubble of the Barents Shelf. The initial detection occurred when the sonar on the Peter the Great identified a massive man-made anomaly. It was a hard shadow, 154 meters in length, resting on a steady heading. This shadow confirmed that the primary hull girder had remained upright. However, the first visual confirmation, delivered by a remotely operated vehicle, revealed a state of structural damage that was mathematically inconsistent with a standard sinking. The AROV cameras, struggling with the high current and low visibility, illuminated a ship that appeared to have been surgically decapitated. The entire forward section, where the first and second compartments were located, was gone, replaced by a jagged landscape of shredded nickel-chrome steel and unexpended missile tubes. The problem of finding the wreck had been solved by the needles of the Richter scale, but the forensic images provided a new engineering paradox. The ROV survey confirmed that the ship was resting at 108 meters, but the wreckage was separated into two distinct forensic zones. The aft two-thirds of the ship appeared remarkably intact, with the rubberized acoustic tiles still clinging to the outer hull. This suggested that the internal bulkheads of the stern had withstood the seismic shock. But the bow section was a mangled ruin of compressed steel, partially buried in the silt. This visual data provided the first clue for the salvage engineers. The ship was found, but it was no longer a unified structure. The search at 108 meters had successfully localized the K-141, but it had opened a crisis of engineering feasibility. The seismic acoustic fingerprinting had proven that the disaster was an event of planetary energy. Yet the upright hull offered a glimmer of tactical hope. The ROV mapping revealed that the ninth compartment hatch, the emergency escape point at the stern, was still accessible. This was the critical finding of the search phase. The ship was no longer a mystery of location, but a problem of pressure and time. The sonar shadows and seismic spikes had led the world to a coordinate on the Barents Sea floor where the laws of buoyancy had failed, and where the mechanical record of the loss was now a visual reality. The localization of the Kursk remains a masterclass in the application of seismic forensics to naval salvage. It proved that, in the modern era, a capital ship cannot disappear without leaving a permanent record in the crust of the earth. The search had narrowed from a 10,000 square mile ocean to a single coordinate on a silt-covered shelf. The coordinates were locked, the visual audit of the external hull was complete, and the stage was set for the most difficult salvage decision in maritime history. The Red Castle was found, and the world now turned its focus from the sound of the explosion to the silence of the ninth compartment. 108 meters beneath the surface of the Barents Sea, the survivors of the Kursk were trapped inside a mechanical environment that was rapidly transitioning from a sanctuary into a high-pressure tomb. Within the ninth watertight compartment, the clock was no longer measured in hours or minutes, but in the rising partial pressure of carbon dioxide and the relentless consumption of oxygen. The ship was down, resting upright on the seafloor, but the engineering challenge of survival had only just begun. For the 23 men who had retreated to the stern post-explosion, the decision to wait for rescue was a calculation of technical discipline performed at 10.8 atmospheres of pressure. This was the initiation of a logical paradox. A machine designed to survive a carrier strike was now unable to protect the remains of its own crew from the simple chemistry of the human breath. The forward compartments were a ruin of thermally warped steel and high-pressure water, but the ninth compartment remained a dry pocket of atmospheric tension. Lieutenant Captain Dmitry Kolesnikov, the officer in command of the survivors, organized the group using a system of manual checks and signal taps on the hull. They were operating in total darkness, relying on emergency breathing kits and the structural integrity of the aft bulkhead. However, the integrity of the steel was a secondary concern to the problem of carbon dioxide toxicity. As the crew breathed, they were exhaling CO2 into a finite volume of air. In a functioning Oscar II submarine, chemical scrubbers containing superoxide blocks would remove the CO2 and replenish the oxygen, but the power was out. The air was turning toxic at a rate that the survivors could not mathematically overcome. To an elite marine engineer, the problem of survival in the ninth compartment is a matter of partial pressure. At a depth of 108 meters, any air within the compartment is subjected to over 10 times the atmospheric pressure of the surface. This increases the density of the gases, making carbon dioxide significantly more lethal. The crew utilized specialized chemical cartridges to scrub the air, but the cartridges themselves required a specific temperature and airflow to function. As the internal temperature of the ninth compartment dropped toward the 4°C temperature of the Barents Sea, the efficiency of the CO2 scrubbers plummeted. The engineering feasibility of the rescue was tethered to this chemical decay. For 72 hours, the survivors were a human sensor array, recording their names and their technical status in notes tucked into their pockets, providing a forensic record of a system failing in slow motion. The salvage decision was complicated by the presence of unexpended ordnance and the mangled state of the bow. The Russian Northern Fleet, and eventually the international Mahmut-Schmidt Consortium, had to perform a high-stakes risk analysis. The forensic survey, which we analyzed in the localization phase, confirmed that the forward section of the ship contained several active Granit missiles and remaining torpedo warheads. The ship was not just a wreck. It was a pressurized bomb. The engineering team realized that if they attempted to lift the ship in its unified state, the mechanical torsion on the shattered forward section would likely trigger a tertiary explosion. This risk was accepted as a mandatory constraint. The bow would have to be severed before any salvage could occur. The decision to sever the bow was a masterpiece of industrial triage. It was a choice to sacrifice the most forensic-rich part of the wreck to save the integrity of the primary hull. The plan involved the use of a custom-designed tungsten carbide abrasive saw. This was not a standard tool, but a specialized hydraulic chain equipped with thousands of diamond-tipped segments. The physics of the cut required the chain to be moved back and forth through the nickel-chrome steel of the hull, effectively slicing through the 15-meter diameter of the ship at frame 0. This would isolate the volatile torpedo room from the rest of the vessel, allowing the reactors and the stern compartments to be lifted safely. The Mahmut-Schmidt Consortium judged this as the only viable path to recovery, a rejection of the unified hull theory in favor of a segmented forensic autopsy. While the engineers on the surface planned the lift, the survivors in the ninth compartment faced the final failure of their internal systems. A secondary internal paradox emerged. The very tools used to prolong their lives may have accelerated their end. Forensic analysis suggests that one of the survivors dropped a superoxide chemical cartridge into the oily water on the deck, initiating a localized flash fire. In a high-pressure environment, a fire consumes oxygen and produces lethal concentrations of carbon monoxide with terrifying speed. The second bulkhead, which had held the Barents Sea at bay, was not the site of the failure. The failure was the atmosphere itself. The 99 souls lost in the forward compartments were joined by the 23 in the ninth, leaving a ship of ghosts to wait for the arrival of the Mahmut-Schmidt Consortium. The salvage decision now shifted from a rescue mission to a recovery mission. The Russian government made the strategic decision to authorize the full extraction of the hull, to resolve the forensic mystery, and provide closure for the families of the 118 men. This was not a matter of economic value. 18,000 tons of scrap steel is not worth the multi-million-dollar cost of the salvage, but a matter of engineering memory. The Kursk was a sovereign territory of the Russian Federation, and her presence on the seafloor was a continuing risk to the security of her nuclear heart. The Mahmut-Schmidt Consortium accepted the contract, and the logistics of the most complex heavy lift operation in naval history were locked in. The The technical justification for the salvage was rooted in the integrity of the S5W-derived reactors. While the bow was a ruin, the central section of the hull was assessed as being structurally sound enough to sustain a vertical lift. The engineers utilized the 26 primary frames of the pressure hull as the attachment points for the hydraulic jacks. By distributing the 18,000-ton load across these points, they hoped to avoid the torsion failure that had claimed other deep-sea wrecks. This was the final engineering gamble, to treat a 20,000-ton cruise missile carrier as a single piece of heavy industrial cargo. The salvage of the Kursk was a rejection of the standard laws of maritime abandonment. The ship would be lifted, its secrets would be extracted, and its structural life would be finalized in a dry dock at Roslyakovo. But the cost of this recovery was the severance of the ship's head. The bow section, with its HTP volatility data and its shattered first compartment, would be left behind in the silt of the Barents Sea. The decision to cut the bow was the final technical compromise, a recognition that in the engineering of naval salvage, perfection is the enemy of the possible. The stage was set for the arrival of the Giant 4 heavy lift barge and the activation of the hydraulic strand jacks. The Red Castle was no longer a tactical asset. It was a forensic load waiting for the physics of the lift to begin. September 2001. The Barents Sea. The most significant heavy lift operation in maritime history was operating under a relentless ticking clock. The Arctic summer was rapidly contracting, and the arrival of the first winter gales would render the specialized salvage equipment of the Mammoet-Smith Consortium ineffective. The strategic objective was the extraction of an 18,000-ton missile carrier from a depth of 108 meters, or 354 feet. This was not a standard recovery, but a masterpiece of industrial logistics and high-stakes engineering. The ship was no longer a tactical asset. It was a fragmented forensic load resting on a volcanic shelf. The recovery was driven by the necessity to resolve the mechanical paradox of its loss and to secure the nuclear isotopes within its reactors. This was the final act of the Red Castle, where the industrial power of the 21st century was applied to the ruins of the 20th. The primary mechanical instrument for this recovery was the Giant 4, a heavy-lift barge that had been radically modified for the mission. The barge functioned as a mobile hydraulic station, equipped with 26 specialized units known as hydraulic strand jacks. To an elite marine engineer, the hydraulic strand jack mechanics represent the peak of linear energy application. A strand jack is a system that utilizes a bundle of high-strength steel wires, or strands, passed through a central hydraulic cylinder. Unlike a standard winch that relies on a rotating drum, the strand jack operates through a sequence of rhythmic gripping and lifting. One set of wedges locks the cables in place while the cylinder extends, pulling the load upward. A second set of wedges then engages, holding the tension while the cylinder retracts to begin the next stroke. The physics of the lift required the synchronization of 26 of these jacks to move the 18,000-ton hull. Each jack was connected to a specific frame of the Kursk pressure hull, utilizing the structural integrity we analyzed in the ship's design. The engineers had to account for the center of gravity and the center of buoyancy as the ship was lifted through the water column. Any imbalance in the lift would result in a localized stress concentration that could cause the hull to snap, a failure mode that has claimed numerous salvage projects. The strand jacks were controlled by a centralized computer system that adjusted the tension on each cable in real time, compensating for the movement of the Giant 4 in the swells of the Barents Sea. This was a battle of synchronization against the erratic kinetic energy of the ocean. Breaking the hull free from the seafloor was the first critical mechanical hurdle. For over a year, the Kursk had been settling into the fine glacial silt, creating a hydraulic seal known as soil suction. To overcome this, the engineers utilized a technique of gradual tensioning. They did not attempt a sudden pull. Instead, they applied a steady, incremental upward force. This allowed the water to slowly seep into the void beneath the keel, equalizing the pressure and breaking the vacuum lock. Once the soil suction was defeated, the 18,000 tons of steel transitioned from a static part of the seafloor to a suspended load. The double-hull buoyancy reserve, which had failed to save the ship from the explosion, now provided a slight mechanical advantage, as the displacement of the intact compartments reduced the effective weight that the 26 strand jacks had to sustain. The transit of the hull from the search coordinate to the dry dock at Roslyakovo was an exercise in extreme caution. The Kursk was suspended directly beneath the giant fore, her mangled forward section leading the way. The barge moved at a velocity of only a few knots to minimize the hydrodynamic drag and the risk of torsion on the lifting cables. This was the slowest and most precise voyage in the ship's history. The engineering team monitored the sensors on the hydraulic jacks continuously, looking for any shift in the internal sediment or a failure in the hull frames. They were moving a nuclear laboratory through a high-traffic maritime corridor, and the margin for error was non-existent. The arrival at the Roslyakovo dry dock initiated the final forensic audit of the ship. Once the water was pumped out, the investigators were able to walk into the 9th compartment and the missile silos for the first time. The visual evidence in the dry dock confirmed the conclusions of the seismic acoustic fingerprinting and the AROV mapping. The forward sections were a ruin of shredded high-nickel steel, but the aft 2/3 of the pressure hull remained remarkably intact. The investigators found the notes from Lieutenant Captain Kolesnikov and the 23 survivors, which we analyzed as a record of human and mechanical failure. These notes confirmed that the survival of the crew in the 9th compartment was limited not by the depth of the water, but by the carbon dioxide toxicity that developed after the internal fire. This forensic data allowed the Russian Navy to finally close the file on the survival timeline, providing technical closure for an event that had been obscured by navigation noise and strategic secrecy. The most critical finding in the dry dock was the evidence recovered from the remains of torpedo tube number 4. The investigators identified the specific fracture patterns in the internal door and the chemical residue of decomposed peroxide. This confirmed the HTP volatility as the primary catalyst for the disaster. The forensic verdict was absolute. The Kursk had been lost to a failure of chemical isolation. The autocatalytic reaction of the training torpedo fuel had initiated a chain reaction that overmatched every safety system on the ship. This finding led to a fundamental strategic shift in naval weaponry. The Russian Navy, and eventually most other major fleets, officially retired the use of HTP-fueled torpedoes in favor of more stable electric and thermal propulsion systems. The failure of the Kursk resulted in a total redesign of submarine ordnance safety protocols, a legacy of safety born from a catastrophic mechanical betrayal. The salvage of the Kursk also provided a masterclass in deep-sea nuclear containment. The 2 OK-650B reactors were extracted and found to be in a state of radiological stasis. The automated emergency shutdown that occurred during the second explosion had been successful. The reactors had remained encased in their heavy lead and steel shielding, resisting the hydrostatic loads of the Barents Sea and the kinetic energy of the lift. This confirmed the technical judgment that nuclear hulls can be recovered safely from the shelf depths if the primary containment vessels remain unbreached. The Kursk was dismantled at the Nurpa shipyard, her high-nickel steel recycled into the Russian industrial economy, leaving only the conning tower as a permanent monument in Murmansk. The strategic legacy of the K-141 is the recognition that the most sophisticated machine is only as reliable as its most sensitive chemical component. The carrier killer was a masterpiece of specialized metallurgy and tactical geometry, but it was defeated by a microscopic weld failure in a training weapon. The recovery of the hull was a technical triumph that allowed the world to read the record written in the steel of the engine room. The Mammoet-Smith Consortium had successfully navigated the ticking clock of the Arctic winter and the physics of the 18,000-ton lift. They had transformed a site of disaster into a localized forensic asset, proving that engineering memory can be salvaged even from the most violent depth. The Red Castle of the Northern Fleet is gone, but the data points extracted from her wreckage continue to influence the design of every modern submarine. The ship stands as a reminder that the ocean is a high-pressure laboratory where every decision is governed by the absolute laws of physics. The Kursk remains a war grave in memory, but her physical remains have been finalized by the machines of the 21st century. The coordinates are empty, the silt has settled, and the strategic silence of the Barents Sea has returned. The engineering logic that judged the ship recoverable was validated by the successful dry docking at Roslikovo, ensuring that the secrets of the Project 949I were not lost to the deep sound channel, but were instead salvaged for the future of naval architecture.